In this lecture, we'll be taking a closer look at the nature of global ocean currents and their impact on global patterns of climate. The second part of the lecture will be focused on the process of deglaciation. So we'll be taking a look at how the last ice age has continued to impact the change over time of landscapes both in the northern and southern hemispheres. We'll begin our look at ocean currents and their impact on global climates by redressing the concept of the Coriolis effect, also known as the Coriolis force. As described in your text, this effect or force is apparently responsible for the drifting of objects as they are moving over long distances, in this case, long distances across the face of the planet. It is the apparent deflection that occurs due to the movement of the planet and the Sun-Earth relationship. Objects moving along east to west trajectories, for example, above and below the equator, will generally be found to drift toward the equator. And this will have an impact in varying degrees on, in this case, water particles and air particles. Now, as you know, wind and water currents are significantly impacted by this principle of deflection. Mid-latitude or subtropical regions within the Earth's northern and southern hemispheres are affected by the process. It will affect patterns of flow as we understand them, as it relates to, in this case, the movement and development of large air masses and pressure cells with regard to the lower atmosphere, but then also the movement of rather large ocean currents both in the northern and southern hemispheres. Ocean currents will actively move away from continental bodies in both hemispheres, and this will contribute to what we know as the Coriolis force. We also know that ocean current movements are responsible for actively cycling, in this case, ocean waters. It allows for the movement of cold, deep water to be brought to the surface or to be made part of surface flows within ocean bodies. And we also realize that it is responsible for the movement of warm surface water into deeper levels. And we know that these circulations of warm and cold water are very much part of the distribution of climates across the planet. Now, the current configuration of ocean currents is not solely affected by the Coriolis force. There are other qualities that will also be factored into the movement of water and what have become our traditional ocean currents geographically. The first relates to the varying densities of ocean waters themselves. Generally, the density of ocean water is primarily the result of temperature and salinity. A second characteristic or factor that is associated with the current configuration of ocean currents is the variation that we see with regard to the depth of our ocean bodies. Another way of looking at this would be to say that ocean currents are also very much of a factor of the topography of the ocean floor. So when we are talking about the geographic development of ocean currents and their connection to global climates, we have to take into consideration not only the physics behind ocean flows, but we also have to take into consideration things like temperature, the chemistry of the oceans themselves, and of course, topography. Unlike atmospheric flows, the circulation of ocean currents does not occur in tight patterns. Both are circular in nature, but generally atmospheric flows are considerably smaller in their geographic distribution. These circulatory patterns, also known as gyres, have distinct expressions of atmospheric pressure at their center, and this will be a big part of how we understand and we are able to ultimately predict not only weather but also storm patterns as well. The movement of water around these centers is also a phenomenon that geomorphologists, as they understand the connection between the oceans and climates begin to take a look at. What they find is that, again, following in the northern and southern hemisphere, there are unique air and water flows, generally clockwise in the northern hemisphere and counterclockwise in the south. The pressure cells that exist at the center of these atmospheric movements is generally high, but we know that this will also vary over time. The process is extremely predictable, whether it's air or water and movement. It has been so predictable that it has become part of our history. Historic trade routes, such as those referred to as the Manila galleons, follow the wind and water action of northern equatorial and northern Pacific currents, associated in this case with Pacific Ocean. Spanish ships leaving present-day Mexico would be able to sail southwest. They would catch the northeast trade winds, taking them across the Pacific to the Philippines and, of course, Manila, where the Manila galleons get their name. They would then catch the westerlies, taking them back across the northern Pacific toward the Alaskan and British Columbian coastlines. Eventually, these explorers and traders would ultimately follow the same currents, but would, in a sense, ride the cool ocean currents south back toward what is today Mexico. So, the unique pressure cells within the atmosphere, the unique systems of flow in both water and air, again associated with many of our ocean bodies, have significant impacts not only on climate, but again, they also are a big part of human history and how we have explored and ultimately peopled the planet. Let's use this diagram for a moment to start taking a closer look at ocean currents. We will start with the equatorial currents. Here we see surface water flow within the oceans, in this case between 15 and 0 degrees latitude. It is generally channeled when you take a look at the diagram. Arrows will generally fall parallel to 0 degrees latitude. That's part of that channelization process. So when you take a look at the Pacific equatorial countercurrent, again, this is a very good example of this channelization process. Also, on the opposite side of the equator, in this case the southern hemisphere, we have the South Pacific equatorial current. This gives us a couple different things here. It demonstrates the very cool ocean, deep ocean water that is being cycled up closer to the surface, becoming part of the equatorial surface flow, and then as it utilizing that kind of Coriolis effect along with ocean water chemistry and the topography of the ocean floor, it bends back down starting at about 22 degrees of latitude south. It bends back down and plunges the warm water deeper into, in this case, the Pacific Ocean, where it becomes part of that west wind drift, which starts the process over again. So again, you see that kind of east to west rapid flow that is part of this channelization process both in the northern and southern hemisphere. With regard to these equatorial currents and the channelization of, in this case, predominantly warm water, we start to see an imbalance in the overall oceanic system. And the imbalance, again, is associated with the amount of water that is existing along our continental bodies or the borders of continental bodies. Known as the Western intensification, this expression is, again, pretty significant. What we see is that there is, in this case, approximately a 15 centimeter by vertical height increase in seawater levels along the western margins of the Pacific and the Atlantic Oceans. And it has a lot to do with the channelization of this warm water. In the northern hemisphere, this western intensification is further compounded by north to south flows of ocean currents along eastern borders of our continental bodies. So in the Atlantic, we see the Gulf Stream, while in the Pacific, we recognize the Kuroshio flow as being part of this north to south phenomenon. Again, you can also see that water temperatures and really the depth of the current will also fluctuate as part of this process. So these become almost natural engines that exist in both the Pacific and the Atlantic Oceans. Another consideration that we have to make when we're taking a look at how these different cycles of ocean currents are created and how they are cycling both warm and cold water, we can also take a look at deep currents. So shallow waters are directed away from continental coasts. However, when we take a look at our the deep currents, these that are moving out into deeper portions of our ocean bodies and then plummeting down, these also become unique kinds of phenomena both in the northern and southern hemisphere. So the shallow waters, as they move away from continental bodies, will actually result in an upwelling of deeper water. And that will kind of bring the cool, deeper water expressions closer to our continental bodies. This upwelling exists off the Pacific coasts of North and South America, for example, and the subtropical and mid-latitude western coastline of what is today Africa. So if you take a look at the kind of western edge of the diagram, you can see in the southern hemisphere the west wind drift that is running generally parallel to Antarctica. Again, the ocean current is deep and it's cold at this point. This will then begin to upwell as it becomes part of those, again, the same water becomes part of the Humboldt current moving along the western edge of what is today South America. As it approaches, in this case, and moves beyond Chile and Peru, along that coastline, we can see that it then is pulled upward or it upwells to become part of that South Pacific equatorial current. A similar pattern can be recognized again in the southern hemisphere as we take a look at that western edge of what is today Africa. We get that upwelling that becomes part of the South Atlantic equatorial current. In the north, again, this is slightly reversed. It's not as noticeable, but if we were to take a look again on the kind of western edge of the map, we see in this case the California current becoming part of that Pacific equatorial countercurrent. And ultimately part of that North Pacific equatorial current, which then brings it kind of back around as it moves toward, in this case, the Philippines and Japan, where it is then brought down into a deeper expression as it moves in that kind of North Pacific drift. So again, it's a very much of a cyclical process, and one that incorporates not only what we're seeing in terms of the kind of the natural circulation of the ocean currents, but also the land bodies themselves, these borders, these coastal regions of our continental bodies. In other areas, there is an accumulation of water which causes that downwelling of water, or in this case, warm surface water. And again, this is something that we can see happening in locations such as the Labrador Sea and margins of Antarctica. So take a look at, again, these kinds of natural cycles and compare them to what we are seeing in terms of where that system of flow is moving and what particular land masses are nearby. What we really see here is that this movement and temperature change as it relates to ocean waters creates a kind of long-term circuit of water movement, taking as much as 1,000 years to complete, but one that is extremely important to maintaining the distribution, at least the geographic distribution, of our varying climates, especially the marine climates. Case in point, in the northern Atlantic water environment, we see it moving downward, flowing deep into the Indian Ocean and the North Pacific. As it moves toward the surface, it is warmed and it is carried in surface currents to the northern Atlantic. The 1,000 year period moves water from the Labrador Sea off of Greenland to its reemergence in the Indian Ocean and then back again. So it's a global system of circulation, and one that has a pretty significant timeline associated with it. And this system of circulation is very much a part of what we realize to be kind of the post-glacial or even really periglacial um, expression of climate change as it relates to the history of the planet. This system of flow, even the storm bodies that we'll be discussing that are connected to it, are considered really to be part of our glacial age and our the process in this case of deglaciation as it continues even today. And again, deglaciation is a process that's really been occurring for well over the last 9 to 10,000 years. So let's incorporate into this brief look at ocean currents the idea of temperature change and deglaciation. As you know, when glacial ice is not present, we're dealing with glacial landforms. Also, as you know from long-term margin areas of glacial bodies to their source areas, these zones of accumulation, geomorphologists will witness a varying degree of deposition and ultimately erosion. Most of our relict periglacial landscapes today are found in areas considered to be marginal with regard to the northern hemisphere and where, in this case, glacial ice sheets existed. The Laurentine glacial ice sheet here in North America is a very good example of that rather. They are also found within areas that have experienced the greatest fluctuation in atmospheric and regional temperature. A common glacial material and process that is associated with these relict areas can be seen in the nature of ice wedging along one-time glacial margins. We see the effects of ice wedging, especially in the kind of northern border of the continental United States. Its border with, in this case, modern Canada, and then also throughout Great Britain, especially along that chalk coast, and of course in northern Europe as well. Geomorphologists consider these relict periglacial environments, especially those associated with what become ice shelves, areas where continental ice sheets are interacting with ocean bodies, to be in very dynamic environments with very dynamic physical events that seem to be modifying them on almost a continual basis. In northern latitudes, we see the impact that permafrost continues to have on land surfaces, and this is especially the case when we still have glacial bodies being present as well. They create, in a sense, weakened geological landscapes. We also see that the glacial environment and this process of deglaciation rather, is something that is very much tied to the moisture levels of the surrounding atmosphere, and it's created what many geomorphologists consider to be glacial morphoclimates, or these local patterns of in this case, climate and ultimately weather that can be tied to the recession of glaciers and the continued presence, at least in the more northern latitudes or extreme southern latitudes of land ice. This can even have an impact on things like erosion, how fast or slow different kinds of physical processes associated with erosion are occurring. So as ice wedging begins to diminish over time, other temperature-related para and post-glacial processes begin to work. And these are things that you have also come across in your readings. Your author describes the mass wasting, for example, that is associated with gelifluction and frost creep. There are other effects that relate to this process of kind of our post-glacial age or deglaciation that's again, naturally occurring across the planet. And this particular effect can relate to fluvial action. And it's interesting because, again, as is the case with the salinity of ocean waters and the greater intrusion of freshwater resources as continental shelves continue to recede, and as they have done again for quite some time, we are starting to see not only an impact in the deep and surface current flows of our ocean bodies, but we also start to see major river systems and their tributaries also being impacted by the temperature change and the overall reduction in continental ice across the planet. So, post-glacial fluvial systems are also things that geomorphologists continue to monitor as the flow of meltwater below receding glaciers continues to impact local landscapes, but then also landscapes that are even very remote in relation to where these diminishing glacial bodies currently exist. An extreme example can be drawn from the landforms, the fluvial landforms that are associated with the Sundanese and Egyptian border in what is today North Africa. Satellite images in the early 1980s revealed buried, very deep flows of water that were associated with post-glacial fluvial actions, even in this area. This is unique because the border between these two countries is really today one of the most arid locations on the planet, referred to as the Salima sand sheet by modern geologists. This amazing, almost desert-like environment has beneath it pretty significant below ground systems of flow. And these, again, are the remnants of glacial waters that continue to move through even groundwater environments. Some of these flows today we understand to be as wide as the Nile River itself, and the Nile and its overall system of flow are also something that very much reflect a kind of post-Pleistocene Cenozoic one-time glacial or periglacial watershed environment. So it's again it's pretty amazing the impact that the late Pleistocene and the end of the Ice Age has had, not only on the ocean currents themselves, their temperature, their salinity, but also it has had pretty significant effects on the landscapes in marine climate environments, and then also inland and even below ground with regard to what kinds of landscape generating processes that they continue to be a part of. So again, it's a very dynamic system, whether we're talking about the currents of our oceans and how they interact with, in this case, the air currents of our lower atmosphere and the amount of moisture in that lower atmosphere, but also it becomes a very dynamic time with regard to the impact that glacial bodies continue to make, even those that are not there any longer, that they continue to make on landform change over time. But being so dynamic, uh, whether it's ocean currents or these periglacial environments, whether they're fluvial or whether they are, in this case, land-based, these become things that are very, very hard to be able to forecast with regard to how things will continue to behave in the future. So, for example, the overall impact that meltwater continues to have, in this case, glacial meltwater continues to have on our oceans and our land forms in both the northern and southern hemisphere. This is something that we can only generate scientific models for, but we are really unable to be able to predict the impact over time. It's something that we have to kind of record in the moment. Another concern that many geologists are having relate to the assessment of global warming as it relates to at least the last 2 centuries of contributions by global meltwater. So it's a very broad topic, but it's something that is very, very important to the work of geomorphologists and especially climatologists. And it's something that, as I said before, is something that we have to continue to monitor in kind of real time as opposed to being able to predict where we might be in the next 2 to 2.5 centuries.